L3 at LEP is really a matter of set zero particles, and set zero particles decay into everything we think is truly elementary today, with one exception, namely the top quark. LEP is the machine in Geneva, Switzerland, which with 27-kilometer circumference has 4 interaction regions, L3 being here, where electrons and positrons collide with energies up to 100 GeV. L3 surrounds the intersection region with a vertex chamber and a huge facet eye of 12,000 crystals of BGO to detect photons and electrons. Hadrons go into the 400 tons of uranium calorimeter, and muons will penetrate everything and be bent under the influence of the 0.5 Tesla field and registered and analyzed in these drift chambers. L3 also is a collaboration of 500 scientists from 42 institutions led by Professor Ting. Technically, L3 is optimized for precision in muons and photons and electrons, such that the resolution is 1% in dimuon mass and delta P over P 2.5%. Since resolution goes linear with B, but quadratic with L, a very large conventional magnet was constructed. The very good, unique photon resolution was achieved by new crystals bismuth germanate. The magnet itself has 140 turns to generate a 5 kilogauss field, and that necessitates a large coil with a hefty wire carrying 30,000 amps. The magnetic field return is done by 8,000 tons of iron, making it the largest electromagnet in the present moment, according to the book of records from Guinness. You see it here in the moment that the support tube was cantilevered in, which carries all other components of the detector. The muon detector, each of these wheels is 95 tons, gently glides on air cushioned, so the alignment of 30 microns is not upset. Here you see it in reality. And behind this is an alignment which the muons coming from the intersection region are measured to 30 microns accuracy in their bend. This was checked under battle conditions from set decays, where you know that the muon should have the momentum of the beam, and indeed, from almost 9,000 events now observed, a resolution of 2.5% as anticipated. Inside the huge support tube is the hadron calorimeter, which stops the hadrons and measures the energy. And inside that, in turn, is this huge array of BGO crystals, shown here, 1/2 finished, 1/2 still being loaded with crystals into the carbon fiber structure. These crystals, for the first time, were grown in equality and length so that the electromagnetic showers could be recorded with 1% accuracy above 2 GeV. It was done in China. The performance can best seen from pi0 to gamma-gamma decays, which is resolved to 7 MeV, the sigma to lambda-gamma with 4 MeV, and the eta, which just was addressed, with 16 MeV. In 1990, the machine started in 98. In 1990, 130,000 Z0s got collected, which gave rise to 35 publications. In 1991, another 300,000 Z0s got recorded, so the total is almost 500,000 now, which gives rise to another determination of precise parameters of the standard model and measures lifetimes very accurately, all in all 60 papers. Let me address just a few of them. We need, as a matter of fact, very accurate luminosity measurement to do precision measurements, which is done from small angle Barber scattering. You can see that the measurements as points and theory agrees very well, so that we can say the luminosity is known presently to 0.6% and will be even better in the future. With that, we can measure, as a function of energy of the machine, the hadronic events and obtain a line shape of a bright Wigner here, which, if magnified, is incredibly accurate. This shows the differential of the values. If you look at events which have strong energy deposits back to back in the BGO crystals, it's E plus, E minus. And you can plot those. They also follow a line shape of the Z0 after the T-channel contributions are removed. If you look for back-to-back muons in the muon system here, again, you can observe the line shape, and the peak of this distribution gives you the partial width. Down here, you see taus decaying into an electron, the other one into 3 pions, which would enable you to measure the lifetime, which was done. They also follow the same line shape. So that we have now very accurate results of this partial width from electrons, muons, and taus down here. Hadronic width is measured here. The width of the Z0 was fitted, and a very accurate measurement of the mass has been done. Now we can ask what is missing. And the missing channels, if you attribute them to neutrinos, you find there are 3 neutrino species in this world, unless they are heavier than 45 GeV. So dark matter has to be searched elsewhere. One also can measure with electrons, muons, and taus, the leptons, the forward-backward asymmetry, that an electron scatters forward or backward. The asymmetry is shown here as a function of energy going through the Z0 mass. The reason this is important is because this asymmetry, if you calculate it from the vector and axial vector coupling constants, it expresses itself in this term, and you can extract it from this measurement and the partial width measurement we have just shown. They are related to the standard model coupling constant with a Weinberg angle. The result of this is shown here. GV, GA on a very enlarged scale. GA is close to the expected value of minus 0.5. These are the 1 sigma and 2 sigma contours. And from this, we can evaluate the sine square theta effective. And from refinements of the calculation of the partial widths, we can conclude that the top mass must be around 196 GeV. Let me come to a test of QED. From E plus, E minus goes to gamma gamma, which has nothing to do with the Z0. In fact, the gammas are strongly peaked towards the beamline and very well described by QED with cutoff parameters which are very high and let you conclude that electron radius is less equal 10 to the minus 18 meters. Also, if you consider gammas from an E star exchange, there is no room for it, and the mass must be bigger than 122 GeV if it exists. Let me switch from QED to QCD, which was now calculated completely to second order. Looking at 3 jet events and looking at the smallest energy jet scaled to the beam energy, we see a strongly falling distribution, which happens to agree to the QCD calculation for a gluon spin 1. If the gluon spin was 0, this distribution wouldn't fit at all. In QCD, we should have flavor independence of the coupling constant. It shouldn't depend on which kind of quark you use. We can single out the heaviest quarks known now, B quarks by large PT muons, and measure for those events alpha S, and it turns out to be the same than for all the others, which is a necessary condition. The thrust distribution, which is the projection of energies on an axis, is known over 4 decades now and agrees with the theory very well. This allows to extract this coupling constant, and the value you find this way is 0.118. However, if you use other methods, you can get higher results. Therefore, we give an average of 0.125 and consider a theoretical uncertainty of 0.08. Search for the standard Higgs is done by looking for set zeros decaying into a Higgs and a virtual set zero, which in turn decays into neutrino, antineutrino, quark, antiquark, lepton, antilepton. This is a process which is completely calculatable. So if the Higgs mass were 40 GeV, you should find so many of this kind of decays and of neutrino decays. So this is the prediction for the various channels. No such event was seen. Therefore, one can say up to the 95% confidence level that the Higgs mass must be bigger than 52.3 GeV. There is an event which is bigger than 52.3 GeV, and which fulfills the topology which we expect from such an event, in that it has a mu plus, a mu minus, and 2 rather broad jets, which could be attributed to a BB bar, and they would form a mass of about 70 GeV. But clearly, the likelihood of such a thing occurring is low, and it needs more events. Charged Higgs was searched for in the tau channels and CS bar. The result is that up to 45 GeV, nothing was found. The following things are unique to the L3 detector and its features. The eta was always a little mysterious, as it was mentioned before. It can be observed with the BGO with very good resolution and high certainty. The spectrum of etas observed in set 0 decays, however, as a function of the relative energy, follows exactly to what you expect, and therefore is nothing mysterious. 3 gammas can be detected very well, and set zeros should not decay into it unless there is a signature for new physics. One event of this type was seen. 0.5 are expected from QED. That lets us set a branching ratio of 10 to the minus 5 for this process not to happen. Hard photons will explore the details of the interaction at short distances. If you compare Z0 decay into QQ bar with a gluon emission, the color string lines will lead to the gluon. If you have a QQ bar with a gamma emitted, the color line goes from the quark to the quark. So you expect more hadronic energy to be ejected in this part here. And this is an energy flow diagram, and the purple line gives you this process, and indeed there is more hadronic energy ejected for this gamma events than for gluon events. And in the other half, it's the other way around, as it should be. So this gives insight into the color string structure, perhaps. Physics of heavy quarks. They can be singled out by muons having a high transverse momentum with respect to the general jet axis of the order of a quarter of the mass. That lets us select very well B mesons from other things, because a cut at 1.5 GeV and PT leaves you only with this red stuff, which is prompt B decays. That's true for muons as well for electrons. Taking only those events with a high PT muon, you can again plot their occurrence, and they follow a Bright-Wigner shape again of the set 0 with a partial width of 385 MeV as expected. Re-extrapolate the muon, the decay muon towards the beam will, since it's a decay, miss the exact beam point by an impact parameter delta. Evaluating that gives you a measure for the lifetime, which is 1.3 picoseconds. From this lifetime, and knowing the branching ratio on how often B's decay to leptons, together with low energy data from CLEO, we can evaluate the transition matrix element from B's to C's to be 0.046. Looking into Z0 decays with mu plus, mu minuses, the invariant mass peaks at 3.1 GeV, showing the J resonance, and the branching ratio for this process is 4 times 10 to the minus 3. Re-extrapolating the mu plus, mu minus to the decay point gives us a measure of the decay time by this distance. This is a different method which agrees exactly to the first one in giving 1.3 picoseconds. Taking these B events and looking by the charge of the muon for the forward-backward asymmetry, we find one which is 0.08, which would allow to extract the coupling constants for B mesons. B mesons can mix. First, normally, if we have a B meson, it will decay only in a mu minus and a E minus, not a mu plus, E plus. The B0 bar, however, will decay into mu plus, E plus. But what may happen with the probability chi of mixing is that this B turns into a B0 bar. In that case, it ought to decay into mu plus as well as the other one. So like sign dileptons indicate that mixing took place. Just counting the events of normal occurrence plus minus combinations and those which have equal sign and therefore could be due to mixing, lets us determine the mixing parameter to be 11%. Lepton flavor violation in C0's decays would signify themselves by Z decaying to, say, a mu plus, tau minus, or vice versa. In that case, if one looks for muons only, one should see muons which peak at the beam energy, and due to the good muon resolution, they should be within this red indicated diagram. As you can see, you only see decay muons from tau events, and therefore we can set an upper limit of 10 to the minus 5 for this process not to happen. Tau polarization. Recording tau plus, tau minus events, the taus are polarized between helicity -1 and helicity +1 states. The measurement of the polarization is important because it determines the Weinberg angle directly. The measured spectrum of taus decaying into pi's and k's is given by these points here. The analytic helicity 1's amplitudes are shown down here and -1 here. They together explain the data and measure the polarization. So from tau to pi decays, the polarization is -15%, but you can do it also from tau to e and tau to mu decays, and with this following results, averaged to a -13% polarization. Other topic is a model-independent analysis of the number of neutrinos, which relies on the fouling effect. Although you create a Z0 which decays in neutrino-neutrino bar, it may have emitted a gamma beforehand, and that gives you a signature that the process took place. The spectrum of these gammas is given by this blue histogram in calculation and agrees exactly with the data if the number of neutrinos is 3. So this gives an independent confirmation. This is a very interesting event we have two of, which was a hard muon, two hard muons, and two hard gammas, which are not close to them. What is surprising about these two events, measured with the extremely good gamma-gamma resolution, the invariant gamma-gamma mass for both of them is close to 60 GeV. And then there is nothing before you have here QED corrections a long distance away. Let me summarize major results from L3 based on 500,000 Z0 events. Number of neutrinos is 3. Lepton radius measured to be smaller than 10 to the minus 17 centimeters, and quarks as well. Mass of Higgs must be bigger than 53 GeV. The M0 mass is known to a very high accuracy, so is the partial leptonic widths. The properties of heavy quarks have been measured very precisely, the decay times of B mesons. The mixing of B mesons has been determined, and a precise determination of the strong coupling constant to second order has been achieved. Unique to L3 are the results that the B to C transition matrix element was measured. In 4 different methods, the sinus of the theta Weinberg angle was determined. An independent confirmation that the number of light neutrinos is indeed 3 was given. Flavor violation in Z decays does not take place. The flavor independence of QCD is manifested by B's. The ether spectrum does not show any anomalies. The unexpected decays like this indeed don't exist. The hard photon emission from quarks agrees very well with expectations and confirms that also quarks are very point-like. The branching ratio into J particles was measured as 4 times 10 to the minus 3, and the mass limit for excited electrons set to over 122 GeV. What will be next? 6 million Z0 events, which allow to search for new phenomenon, as the last mysterious events I showed you. Precision tests of the electroweak theory. In 1994, the energy will raise to 200 GeV or above and enable W plus W minus production with this luminosity in 3 years to test electroweak theories further, make a Higgs search up to masses of 80 to 90 GeV, and search for new phenomena. The W plus W minus production is interesting in that it can proceed with the following 3 diagrams, of which this one is specific to the non-abelian nature of the standard model. together, they give the very Mannerly cross-section shown here. If this graph wouldn't exist, they would raise to very high values. This is even demonstrated more in the angular distribution, which the decay muons from these W's would have with respect to the beam axis, cosine here. In the standard model, you expect a very steeply rising angular distribution, whereas if this graph doesn't exist, it would be very much flatter, and you see many more events in the backward hemisphere. After all these successes with the standard model, let me remind you that the standard model has 20 undetermined parameters, which have to be taken from experiment, namely the coupling constant, the lepton masses, and the quark masses, and the mixing parameters. And 13 of those come from the so-called Higgs sector, which has to be explored in future. And that I will leave to Greg Hurton. Because if you plot these masses on a strongly logarithmic scale, you see that they are all raising upwards, and something ought to happen in this region. Thank you.